This is an overview of the Arduino Mega based DC motor kit. The basic motor has a disc on the end, then encoders on the back that has 334 slots. There's two headers for motors. There's a DRV8833 motor driver. There's a potentiometer to do some labs where you can rotate the potentiometer a certain amount and the disc can rotate a certain amount. There is an option for external voltage input if you want to do something more than 5 volts. But for the most part, all the labs are designed for 5 volts. If you're using external voltage, there's a switch for your externally supplied voltage, and there's a switch to go from USB to your battery voltage. If you're not using an externally supplied, you leave the battery switch off, keep it on USB, and there's a switch to easily turn off the motor if you need to. That turns the driver on and off. The microprocessor is a Arduino Mega, and it has a normal USB serial converter, so when it shows up in Device Manager, it's just going to show up as a COM port, serial COM port. So in this case, if I plug this device in, I would see it as COM11, it's USB serial CH340. That's what it'll show up as when you plug the device in. This is an overview of the code with it. There's 2 example codes. One is just getting the velocity, the step response for the motor to a step voltage input, looking at the velocity. That way you can figure out the transfer function or the model for the motor. And once you know that, you can design a compensator for it. So this is velocity control, PI compensator. If we look at the velocity step response code, this code is modified quite heavily with Python to add some of the GUI stuff. But the basic code is all the setup for all the pins. There's a setup for the amount of data to send, so you can actually use a serial plotter. So for getting all the setup stuff, there's also stuff for the encoder. So all the encoder processing is done on the Mega. That way it keeps track of the pulses. The functionality is meant to mimic the way it appears in Simulink. So in Simulink, there's a block that goes from voltage to the PWMs for the motor. So there's a function here to sort of replicate that structure. All the normal pin setups. Once you get into the main loop, there's something that keeps track of the loop timing. It reads the position of the encoder, calculates velocity and velocity from the previous position. And it's using quadrature encoding, so it's 4 times the number of pulses. There's 336 pulses. Creates a reference waveform for the velocity, and then essentially goes from 1.5 volts up to, and this is voltage reference, so it's going to go from 1.5 volts, whatever the voltage reference is, somewhere up here. Voltage reference is 2, so it's going to go from 1.5 volts to 3.5 volts. So that'll be the step response for the motor. And you can see that the motor is going from high speed down to a lower speed. And that's essentially all the code is doing. It's going to apply that voltage to the motor. There's 2 different ways to look at the data. One is using just writing velocity and the voltage scaled by 10 to the normal serial port. So once you have this running on the system, just push download. This is the velocity step response. Then you can go to tools and serial plotter. And you'll see the blue is the step response of the velocity. The red is the voltage, because we're not sending, in order to make this appear nice, it's only sending every 10 samples. That's why it looks like this isn't a step input, but it actually is. So this is just so that you can quickly run it, make sure that everything's running okay. If you want to get the data at a high rate and be able to visualize data at a high rate, we're going to use a Python GUI. And that's what the last part is. It will send the data in binary, so it can be plotted with Python. So you have to go up top, change the data output so it outputs it, so we can read it with the Python GUI. Just download it, and then you're going to open the velocity reference plot. So if you open this, if it doesn't connect to the right port, you might have to refresh this, and in this case it didn't connect. Go to COM11, and then I can try to reconnect and unplug it. And if it doesn't connect after trying again, it's because the Arduino IDE, even though it doesn't show that anything's open using the COM port, serial plotter ends up blocking it. So you just have to close down the IDE, and then we'll open that file back up. As long as you don't open serial plotter. So if you know you're not really going to be using serial plotter, that's just a quick check, then don't use it when you open this up. Make sure that this is set to 1. We can then download it. And then once it's downloaded, then you can use the GUI to connect. So I can disconnect and then connect to COM11. So now we can see that the code is running. It's doing the same step response. So the step response data is in yellow. And at this point, you could tune. So it's going to also plot what the theoretical result is for a model, which is k over tau s plus 1. So if we actually change what we thought the model was, let's say we thought it had a steady state gain of 50 and a tau of 4, we would see that our model, which is the magenta, isn't matching what our data is. So we can actually tune our model parameters and do the parameter ID. I think it was 59. And we'll see that changes the steady state gain, which is good now. But now you can see that the time constant isn't matching well. If we change the time constant to 80 milliseconds, then we get a pretty reasonable match for this. We can also change the predicted behavior is going to include the steady state offset from Coulomb friction. So we can kind of adjust how much Coulomb friction there might be, and that will slightly change the predicted model. So here now we can see we have a reasonable shape. So tau is pretty good. Steady state gain is pretty good. So now we can assume that our model is 59k over tau 0.08s plus 1. This also shows the reference. The reference is the voltage input, but it's scaled up by a factor of 20, just so it's really easy to see on the graph. So the voltage in, and then the step response out, the data is in yellow, and the magenta is what the model predicts with a k and tau shown here. So we can use that step response to get our model, and then we can do our controller design. So for our controller design, the example is a PI compensator, and it's going to be there'll be a part where we can run this PI compensator using serial plot, but then we'll have to restart the IDE, but we'll do that first as a quick check. So if we go through this code, we don't want to use the GUI first. We're just going to use Arduino to make sure this is working. Again, after all the normal setup, it's doing all the encoder stuff. The main loop is somewhere in here. The main loop calculates velocity, reads position, generates a step reference in speed. That reference, if we scroll to the top, I believe it's going to say, I want to achieve a reference speed. Where's the reference speed? A reference of 200 radians per second. So that's the reference that we want our desired speed to go to. We have a max voltage of 4.8 volts. All this is setup stuff. If we go down to the main loop, it's going to create a step in reference. And you're going to calculate the error by the reference position minus the measured velocity, integrate, and then apply our PI compensator. So in this case, it's proportional. There's a pole at the origin. There's a 0 at, if we look at where Ki is defined, there's a 0 at minus 47. So this is the only code for the PI compensator, and then we apply it to the system. So we're going to run this. Let's just make sure that it's set up to do Arduino plotter, which it is. So now the motor is going to go from 0 speed up to 200 radians per second and stop. If we want to quickly make sure that the data looks okay, we can go to serial plotter, and it shows that that speed's going up to 200. You notice the serial plotter is not great because it doesn't really allow you to control how much data is available. So we're actually sending, that's somewhere in here. We're not sending data every sample time. In this case, it's 2 milliseconds. We're sending it 8. We're skipping 8 samples then sending data. So if you want to slow down the graph, you could change the decimation, how often you send data. Just delay a larger amount of samples so that that serial plot looks a little better. But that's just quick verification. In general, probably won't be using that, or you could. But if we want to use the Python GUI, this will download, but chances are it's not going to connect because that serial plotter is going to be blocking our Python GUI. Let's see. So we want to plot the PI, the GUI for the Python comp. So yeah, so it failed to open. So we just have to close down the IDE. Once that's done, then we can connect. You could open it back up. We'll connect to COM11. And now you can see that this is the data's in yellow again. And if we want to get the predicted response, we have to indicate what our K and tau is that we just identified for the model. And then we have to use the same KP and KI gains that we used in our controller code. And then now that it knows the controller and it knows the model, it will predict what that response is. And in this case, we can see we get a pretty good match between our theoretical and our actual step commute. Of course, you can change all these as it's running. There's also options in this one to export this data that's being sent because it's being sent at a high rate. This GUI was generated using ChatGPT. So if you wanted to add that to the other plotting code, you could just paste that whole entire Python code to ChatGPT and ask it to export. Actually, if you paste both of these files, you could tell it to modify the first one so that it exported data similar to this file, and you could get that. If you don't know how to do that, you can always just let me know and I can do those things. So that's the basic overview. That's the code, and let me know if you have any questions.